Hey everyone, welcome to our fifth lecture on causality for AI and ML. So we will start with a very short recap on the last lecture, and then Florian will present you the topic of causal discovery. So I just want to repeat some of the exercises we had in the last session. So we had this causal graph, and the question was using the rules of vector adjustment to find adjustment sets that will allow us to get an unbiased estimate of the effect of X on Y. And yeah, I think we discussed it a bit in the last lecture, but maybe some of you looked at it again and have some ideas what could be like some of the adjustment sets, and then what are the minimal adjustment sets that are needed to adjust for this. So again, in this adjustment set, we can have no descendants of X, and it needs to plot every path between X and Y, so every vector path in this graph. Has anybody an idea or like a suggestion what variables to choose? Yeah.
Either B and Z or Z and C.
Okay, so B and Z or Z and C. Yeah, they and why exactly those?
Because they block the information flow from X to Y.
Mm-hmm.
Paths.
Yeah. So which kind of vector paths are there? So you said either these two variables or these two variables. Yeah. Any other ideas for possible adjustment sets? Okay, right. So basically that's the thing. I guess it's somehow wrong, or not wrong in the thing, but we can have one additional adjustment set. So basically the idea is to plug this vector path from X via Z to Y. And then because we need to adjust for Z, we open this collider structure between A and C. And therefore, to plot this path from B via A, via Z, via C, we also need to plot this via adjusting for B or C.
Slight correction here. Or alternatively, we can also adjust for A. So any subset of the set ABC is a valid adjustment set because any of those variables blocks the second path that is opened by conditioning on set. So any pair set A, set B, set C, or any of the additional variables are suited to serve as an adjustment set in that case.
Okay, so, well, I've written down the solution. I think it's easy to check for this. So deriving the vector adjustment via the rules of do calculus. So it's quite, let's not say easy, but of course, at the beginning, we can destructure like our probabilities according to the causal graph. If you have any questions on that, I think we will answer them then afterwards or separately because you need some time. But this is like standard probability theory, nothing special. Then we just need to get rid of this duo X in both of these terms. Basically, what we discussed in the slide last time for this later term, that because X has no effect on Z, we can just drop it. So this is rule 3, right? There are no causal paths from X to Z. So it's in the anti-causal direction. And again, for the first term, because Z blocks all the vector paths from X to Y, we can drop the do operator there and just replace it with simple conditioning. So maybe if you want to look deeper into that, maybe look at this derivation and check whether the rules or the conditions for applying these rules hold in this graph. I've written stuff down. There is a long way to do it and a shorter way to do this first step, but we will provide also extra material where we go into that in detail.
All right. So hello everyone. My name is Florian. I'm also part of the PhD group at Grid Casting, also researching primarily on causality. And yeah, topic for today is causal discovery. Quite a broad topic. We've got a lot to cover, but please always feel free to interrupt me if you either have questions or if I'm just a bit too fast, like content-wise or speaking-wise. So please always feel free. Yeah, other than that, let's get right into it. Let's start with some basics and motivation. So generally, causal graphs can be very useful, right? You know that, and Mahidi was kind enough to help prepare a small motivating example for that. So let's say you want to know whether you want to go to Mensa or not. Then this obviously depends on multiple factors. For example, how much the current cost of döner currently is, and also whether Mensa currently affords spices or not. To be a bit more detailed and get more information, we can also go a bit further than that and look at the current policy situation. For example, will Merkel make döner per euros again? Because in that case, the current cost of döner will probably be much cheaper. And on the other hand, there's probably something that influences both the cost of döner and the Mensa spice situation. I'm not an economist, so economy or something vaguely, right? But we can be sure there's something that influences both of these things. So let's say we have that example, right? This is not new for you. You can ask probabilistic queries. What is the probability that I go to Mensa today, given that Merkel made döner for €3 again? Causal queries. If we intervene to provide lots of spice to Mensa, does the cost of döner change? And we can determine causal effects. You've heard about that last week, too much more stuff. All because we can use the causal structure given by the graph to do various kinds of inferences. So if we have a graph like that, right, variables are determined by their parents, but being determined doesn't mean that information only flows in one direction. Because if we talk purely on a correlation basis, so not necessarily causal, these separations showed us we can also have an information flow in the anti-causal order as well as in the causal order. However, talking about causality, talking about effects, this is only downstream, only following the arrows, following the causal hierarchy. And yeah, that's when we deal with interventions and then maybe even also counterfactuals. Okay, let's come to the big part for today. In practice, we might not know the causal graph, though. We can do a bunch of cool stuff with the causal graph, but we might not know what the structure even is, what edge there should be. And in that case, I'm sorry, let's go one step back. Get that. One obvious possibility, if we can, let's just do what I just did, have experts provide the edges. If they're really experts, if the application is clear, I mean, that's perfect, right? Then we are done. But in practice, especially from the machine learning point of view, where we want to apply causality to a bunch of new data sets or so on, it can be quite expensive and also unrealistic, because even if you imagine a setting with 100 variables, sure, experts might be able to tell you, yeah, this has a causal influence on that. But that doesn't mean there's a direct edge, right? Because it can be a complicated long path. So always relying on experts on all situations is definitely not the way to go. Today, right, the last few years have shown LLMs can do a bunch of stuff. So maybe we can just query an LLM. This is done, this does happen, but it's clearly not always optimal. I will talk a bit more about that towards the end of the lecture. But for now, let's just believe me when I say you don't always want to do this. And for the majority of this lecture, this is also not what we're going to focus on. So as we're a causality and machine learning course, the main focus here is the data point of view. So we have a bunch of data. We have our tabular data sets. Can we discover causal relations from data alone? And that's what causal discovery is, or to put it a bit more formal. Let's say we have a set of graphs defined over a set of variables and a data set. And unknown to us, there is one G star, one true but unknown graph. And this graph was responsible for generating the data that we are seeing, right? The data we're seeing in machine learning. And then the causal discovery problem is the problem of recovering this true graph given the data set. Also a note for the future lectures. As you see here, we have a definition over the variables v. It is another problem to actually find out the variables v in itself. And that's called causal representation learning. To just give you one example, if we say we're interested in causality over images, then if we don't have any additional information, we could like put each pixel as a variable, but that doesn't seem very useful and it wouldn't be. But then extracting, like disentangling these variables from different representations is called causal representation learning. So that's basically a step before that, where we even have to uncover the variables. But the task of causal discovery that we are looking at today is specifically the one where we have a specific set of variables. These are known. We know the nodes in the graph. We just don't know how they connect to one another. All right. Then another big point you heard a lot about in the previous lectures is acyclicity. Generally, like you can do causal discovery on non-acyclic graphs as well. This is generally also the much more difficult problem. And most applications and like methods and algorithms focus on the DAG setting, the directed acyclic graph setting. We'll also do that today. I have, I think, one slide, maybe two towards the end, that takes a short look at what it actually could have cycles. But if I don't say anything else in the course of this lecture, feel free to assume that we're dealing with acyclic graphs. This makes our life much easier and is also much more useful in practice. So yeah, if you have these like cyclic dependencies, we're not taking a look at that today. All right, that was pretty fast, but I hope most of that wasn't pretty new. I'll try to slow down a bit now and then hopefully can all follow along. Again, feel free to interrupt at any time. But actually, we'll have a little bit more of a like reminder from the previous lectures. So to get into the first big topic, you know, deseparation. Deseparation tells us that the graph induces specific dependencies. For example, if we have variables that are not independent, for example, during an spy situation, then we know there must be an active trail. In this case, we can see that trail connected by the through economy. So this is why these two variables would not be independent. On the other hand, we can have independent variables. For example, in this example, the Merkel and economy situation, there would be two active trails, but both are blocked by V structures, one at the Döner and one at the Mensa situation. So this is why these variables would be independent. But for these independent variables, if we have a V structure that connects them and we then condition on that, suddenly they're becoming independent. And yeah, so we know all of that. So basically, we know that there are dependencies and independencies shown by both the graph and the distribution. Can we utilize that somehow to identify our true graph? For example, let's say we have a very simple two-variable problem, A and B, and these are not independent. What do we know about like three possible graphs here? Do you have an idea?
The first one or the second one?
Exactly, the first one or the second one. In that case, we can conclude, okay, yeah, it can't be the third one. They're not independent, obviously. That's like the simple example here. But as we also see, yeah, this pure independency or dependency rather doesn't tell us the specific graph yet. So it's not that simple that we can always get the full graph just from doing like some independency tests, but it can definitely provide us information to do something. But then if we have that, does this mean we can remove like some possible edges? You know, we know some edges might be there, might not be there. But does this mean there's like no way at all in getting any directed edges? Or could there still be a way how we actually find directed edges even purely based on independencies?
I mean, you can find out from these structures.
Right, exactly, V structures. So that's going back to deseparation. If we have these figures like on the right, so we have a V structure, meaning A and C are not connected, but they have a common child B, then this structure has a set of dependencies where A and C are independent, but they become dependent given B, that is only supported by this specific causal structure. So if there was a chain A to B, B to C, the other way around, or even like a common cause, B causes A, B causes C, this would have different independencies or dependencies. And in this other case, we couldn't actually direct. Like if the dependencies were the opposite, then we could only draw edges, but not direct them. But in the specific V structure case, we can even can not only draw undirected edges, but even direct them immediately. That's pretty crucial to the PC that I'll get to in a second. Idea, questions on this particular case? All right, and yeah, and then basically the next idea, how we can also do some directed edges, is following the acyclicity assumption. If we have a chain A to B, B to C, and then we have another edge A and C connecting, we know that this edge cannot direct from Z to A simply because that wouldn't use a cycle, and that's against our assumption. Simple as that. Obviously, for the acyclicity case, we need some directed edges before. Only that will not give us the first directed edge. But just this fundamental idea of figuring out where these vectors lie, getting some undirected edges for other relations, and then applying acyclicity and some other ideas that I'll get to in a bit, no worries, can actually tell us a lot about the true graph. Okay, might be the last reminder. You had heard about these assumptions before. The Markov condition tells us that any independency in the graph must be an independency in the probability distribution. Faithfulness tells us the other way around. If we put both of these together, assume that both of them are true, then we have what's called a P-map, meaning that the independencies of data and graph are completely shared. These seem like two very useful assumptions if we do causal discovery that way, and that's why the algorithm that I'm presenting now, the Peter-Clark algorithm, or short PC, assumes those to be true. So let's take a look at the assumptions. Again, as most of the time in this lecture, we'll assume that we have acyclic graphs. And then we also assume the Markov condition and faithfulness, what I just repeated in the last slide. So we assume that every independency we observe in the data would also be observed as an independency in the graph. Okay, what should be new to you is the so-called causal sufficiency assumption. And this is another assumption for this algorithm that basically says for a population, causal sufficiency is true if and only if any two or more variables in V either do not have a common parent or this common parent is constant. So let's maybe immediately jump to a small graph. So let's say our data set consists of the variables A and B, but there is another variable, U, but U is unobserved. So U is not part of the variables we are seeing. If we would do causal discovery on this very, very small example, right, where we have data over A and B, what would our independency tests tell us? Any idea?
Yeah, dependent because of the confounder.
Exactly, right? We have this common parent structure, the what's it called? Fog structure that induces dependency. A and B are not deseparated; they're clearly dependent. However, neither A is a cause of B nor B is a cause of A. So if we assume that there, so if we want to put an edge between those, neither direction would be correct. So we would have a different edge that tells us something well, this is confounded. Maybe a more practical, maybe a not more practical example could be something like this. Leave it up to your own imagination whether that's true or not. But just to repeat the intuition, also if you want to look at the slides later. So basically, if sufficiency is not true, then variables that should be independent, given the independency assumption that we take from the data, still appear to be correlated. And I mean, appear to be is maybe not the best way to say this because they appear to be and are correlated. But then this cannot be fixed by drawing an edge from A to B. This can also not be fixed by drawing an edge from B to A. So if we assume that there's some true causal graph where every edge is directed, then without sufficiency, this would be a big problem. Yes?
Just be rephrased as there being no hidden confounders.
Exactly, yeah. There's no hidden confounders. That's exactly it. All right, let's jump into the algorithm then. So as I said, machine learning perspective, we have a data set, let's say m number of samples, n number of variables, and we want to discover the causal graph. The PC algorithm has a specific output called a CPDAG. Has that been mentioned in the previous lectures? Okay, so CPDAG short for completed partially directed acyclic graph, and this basically represents a Markov equivalence class. So in a CPDAG, it might be that some edges remain undirected. However, this for the PC algorithm, for the CPDAG, this undirectedness does necessarily imply that one of the two directions must be true. So if you have an undirected edge between A and B, then either A is the cause of B or B is the cause of A. This does not mean that there could be a hidden confounder in that case. So that's important to keep in mind. So for example, if our true graph is A causes B, then the corresponding ZPDAC would simply have this undirected edge between A and B, because purely based from dependency and independency, we wouldn't know what the cause or what the effect could be, but we could figure out that they're correlated. Clear so far?
Then you only detect the skeleton, and you also detect the V structures, because that doesn't that's not covered by the Markov equivalence.
The Markov equivalence class covers V structures. And basically, the Markov equivalence class contains all graphs, so where all edges are directed, that share the same set of dependencies and independencies. But then for V structures, there's only one possibility how a V structure could look like, right? For dependency and dependencies. But then if you have like just two variables or chains of forks, then there are multiple possibilities. So then these multiple possible edges are basically overlapped in quotation marks, if you will, and turned into an undirected edge. All right, so let's get right into it. So the PC algorithm can be like simply divided into two phases. Phase one, skeleton discovery. So that's also what you meant, right? We have we identify all edges, like all undirected edges. So basically we remove all edges that shouldn't exist from the graph. And the rough idea is to start with a fully connected graph and then do a bunch of independency tests to figure out which edges cannot possibly be part of the true graph. And then this leaves us with the skeleton. And then in the second phase, we have the true skeleton, assuming the algorithm worked correctly. And then we're checking again for V structures. Here what we're doing is, so V structure, by definition, right, must be like a triplet, A edge to B, B edge to C, but where there's not an edge between A and C. And then we can direct this triplet if and only if B was not part of the conditioning set that was used in phase one to establish independence between A and C. Because we know there must have been some conditioning set that established independence between A and C, because they're not connected anymore. But then from that actually follows that this must be a V structure. Feel free to ask questions on that, like on a future lecture. For now, as long as you accept that this is true, let's continue for today, and feel free to ask questions on that, like at another lecture. But I have to take a bit of a look at the time, so that's why I'm not going to like full detail here. Last step, meek rules. That's the name for like a set of rules that direct edges where we, from like other logic, for example, acyclicity, can infer that only one direction is possible. I'll have an example, and then feel free to ask questions.
What do you mean by unshielded?
Unshielded means that there's no edge between A and C.
Ah.
If there was an edge between A and C as well, this would also be a triplet, but it wouldn't be unshielded. Okay, let's take a look at a different example. Present attendance at the lecture. Let's say there's a duration of a gaming session the day before, and as the diligent scientist you are, you record how long that was. But you think there might be also other factors in play. For example, your caffeine consumption on the day before, your sleep quality, maybe you have like some watch that keeps track of it. And then in the morning, whenever your alarm goes off, you like tick a box. How high is your motivation to get up? High, low. Maybe if it was low, you fall asleep again. Maybe not. But let's say you create a big data set about that and want to do some science. In the end, there's obviously the presence of the lecture. You can record all of that. You have your tabular data set. So that's roughly how your input to the causal discovery method might look like. But you have no idea about the causal relations. So let's apply PC. One small side note here. Whenever we do independency-based stuff, if you're actually doing that, be careful about using the right dependency tests. We have different tests for discrete variables, continuous variables, mixed variables. This is not the focus of this lecture, but if you're actually applying that, don't forget to pay attention to that, because using the wrong dependency test will obviously simply lead to false results most of the time. But for this lecture, we're just assuming that all independency tests give the correct results. All right, PC, step one, fully connected graph. So basically this is this here, no edges directed yet, everything is possible. Now we're starting to do dependency tests. We go over each pair of variables, so coffee, gaming, not independent. Coffee, motivation to get up, not independent. Coffee, lecture attendance, not independent. Continue for each pair and actually find out a single independency. Doesn't look good so far. So let's go to the next step, conditioning on one variable. Does anyone have like one example what a like plausible independency by conditioning on one variable would be? Give it a try.
Condition to get out of consumption condition on sleep quality. Yeah, sleep quality.
Mm-hmm.
I will explain both. Really.
Okay, so coffee would be independent of the motivation to get up given the sleep quality.
Yeah.
Yeah, that makes sense. To be fair, in my example, I put it a bit different. So let's see if you can also accept like my justification, but definitely the right train of thought. So what I argued is, okay, let's say coffee consumption should be independent of lecture attendance given the motivation to get up. I mean, this example might be intuitive, it might not be. Obviously, we're assuming that we get all of this from data, right? But in this case, okay, we have this independency, it was established by conditioning. Let's remove that edge. Next one, gaming and sleep quality. Oh, seem to be independent if we condition on coffee. Away with that. Gaming session and lecture attendance, again, if we condition on the motivation to get up, that seems to explain it well enough. Same for sleep quality. Well, they are correlated if we don't condition, but then the conditioning on the motivation seems good enough. Remove the bunch of edges. Can we get any more if we condition on two variables? So here in this fictional data set, we can establish an independency between coffee and the motivation to get up, but only if we condition not only on sleep quality, but also on the gaming session. Right. Then that's all we have. Generally, we really need to like stack the conditioning sets up. There's like some smart strategies you can do to not have to test for like every possible set. But generally, yeah, can be quite expensive to do all these conditional independency tests because it's not sufficient to stop at simply conditioning on a single variable, which hopefully is clear or maybe might become clear from the true graph soon. Okay, so that concludes step 2. We have our true skeleton. Now we're taking a look at these structures. So our triplets. We have a bunch of unshielded triplets here. We have like coffee, gaming, sleep quality. So basically in this like square, every like triplet that connects each other would be an unshielded triplet. We would have another one at sleep quality, motivation, and lecture, another one at gaming, motivation, and lecture. But in this case, we find that if we take a look at this particular triplet, then we had removed that edge in the previous step by conditioning on coffee, but not by conditioning on the motivation to get up. Following the PC algorithm, this means that since this variable was not in the conditioning set, that must be a V-structure. Maybe now my like food for thought question from a bit earlier might be a bit more intuitive here, because to like give like a very brief response, if we have a V-structure here, right, then this triplet, this part alone, if we consider it in isolation, means that gaming and sleep quality are independent. If we would ignore everything else, we basically can ignore everything else if everything else is conditioned away. But since this didn't need to be in the conditioning set, but we still have a path, then this path must be a path that doesn't lead to dependency, that isn't like connected using like not deseparation. Hope that was kind of clear. In this example, though, that's the only V-structure we detect. We make the test for all other cases, but they appear to be false.
But here you're assuming that we already eliminated all the dependency, all the dependencies in the last step?
The first step, like the first 2 steps, they correctly remove all the edges that shouldn't be part of the graph, assuming your data is good enough and so on. Okay, and then the last step, meek rules. This is a set of rules that we iterate over to see if we can direct any other edge. And here we actually have one edge that we can also direct. Consider this edge going from motivation to the lecture attendance. Let's assume the true edge would have to go from lecture to the left. In this case, there would be a V-structure between like the sleep quality, the moon, and the lecture attendance, right? If this was an edge, then that would be a V-structure. However, just in the previous step, we know that we should have taken care of that if that truly was a V-structure. We should have detected that in the previous step. So just by removing that possibility, we know must be the other way around. Direct that in the other direction, get another edge. But even if we iterate through the full set of meek rules, it turns out that the top 2 edges are not directable using the PC algorithm. So then this is the final result. This is our CP-DAG representing the Markov equivalence class. So purely based from data, it could be that the true graph has outgoing edges from coffee, but it could also be that there's like gaming to coffee, coffee to sleep quality. We just don't know that. Right, maybe before we get to that, questions on the PC algorithm.
We move on. I think that there was one question, and that is here we always have independencies because we know what the variable is. If we're doing that algorithmically, then we don't exactly know how
This
it
is-
means. Then we have a kind of a combinatorial explosion, which makes the algorithm not tracking.
The algorithm might
How do we
even
know which independencies to test for?
data. I mean, we will basically brute forcing everything. That's like the fundamental idea. And then in practice, we don't need to do some more tests once we've discovered some stuff, right? If we already removed an edge, we don't need to condition on more variables for that pair of variables. So we can be a bit smart about that. Generally, I mean, like a lot of detail going into that. But yeah, it's expensive. If we have big problems, the conditioning sets grow, it scales terribly. That can be a problem for PC. All right, fun exercise that we can then like present next week. Let's go back to the first example. And here the first task is basically a repetition of the previous lecture. So let's say we have this graph, write down all pairwise and conditional dependencies for that displayed Mensa graph. You can ignore all independents that do not have a minimal conditioning set, which means if like two variables are already independent, they're not conditioning on anything, then you can stop there and don't need to consider any other sets where you condition as well, they're still independent. So task 1, get all independencies here. And then let's consider the PC setting in which we don't know the graph. Imagine you multiply the PC algorithm here. So usually you would have data, you would apply independency tests, just so that you don't have to write code to simulate that. Let's just use the independencies you figured out from the last example, from the last exercise, I mean, from the last slide, and then apply the PC algorithm on that. How does the final CP-DAG look like? Yeah, feel free to try that out. I think it's a good exercise, and if you got that, then you can probably deal with the PC algorithm well. All right, meet rules. So the underlying assumption behind meet rules is basically that both acyclicity is true and that all these structures have been identified before. So if we take a look at this graph here, just based on logic, what do you think could be, like there are two undirected edges. Can we direct one or both, and how? Can raise your hand, please, so that other people might also be able to chime in the future. But that's true. So D2C has to be true simply because otherwise we would have the cycle DB, DC, CD. However, even if we think more about it, the DE edge actually remains to be not quite clear. It's not that there's a potential V structure into V. We can't really conclude anything from that. So that's where we would end here. That's the full set of rules. Feel free to think a bit about that if you want. Maybe just one small hint there as well. If you consider stuff like the second rule, don't be confused that we are basically creating a V structure there, because we're not, right? It might look like we're creating a V structure, but since both the parents, the left nodes on root 2, are connected themselves, this is actually not a V structure. So always keep in mind that the V structures must have like independent parents. So root 2 is not about creating a V structure. It's purely about like taking care of acyclicity. So that's why root 2 is not in conflict with rule 1, even if it might look like that. But if you weren't even confused about that, then perfect. Then it's all good. Right. So I introduced the causal sufficiency assumption that deals with PC. Just the same assumption I had before. In short, no unobserved confounding, as you said correctly. Just one like food for thought for after the lecture if you want. Why do we even need an assumption on like common causes, unobserved confounders, but not an assumption that there are no like unobserved children or unobserved mediator variables? Because we don't have any assumption on that, and we also don't need one. So feel free to think about that if you want. But now, focusing on sufficiency again, let's take a brief look at another algorithm where the causal sufficiency assumption is dropped, namely fast causal inference. So here, same set of assumptions, minus causal sufficiency. Again, we have a data set, but the output is now called a PAG, partial ancestral graph. So this means we have 4 different types of edges here. Namely, we still have the, let's call it like normal edge, if you will. A is a cause of B, pretty clear. But then here, if we have an edge that has arrowheads into both directions, then this does not imply that A causes B and B causes A, because that would violate acyclicity, right? Then we would have a cycle. But it instead implies here that there must be a latent common cause, so that there is some unobserved variable U that causes both A and that also causes B, but that there is no causal effect from A to B or from B to A. And that's what I meant with PC before. We need new kinds of edges if we want to like argue about causal sufficiency. So that's how FCI is doing that, by adding these types of edges. And then the small circle in the third and fourth example basically means this could be both an arrowhead or not an arrowhead, or a bit more semantically, this means either this turns into not an arrowhead, so A is a cause of B, or this turns into an arrowhead, so we have a latent common cause. And this or statement is basically equivalent to, well, I mean, B cannot be like a cause, direct or indirect, or an ancestor of A, but we don't know whether A is a cause or whether there's a latent variable. And then the last one is even more general. A could be a cause of B, B could be a cause of A, or there could be a latent common cause. We don't know all of that. We just know that they're not independent, even if we condition on other variables. FCI implements a set of like 10 different rules. I couldn't even tell you all of them from the get-go if I wanted, so let's save some time here, but feel free to take a look, of course. The general logic and idea and motivation behind the algorithm is the same as for PC. All right, so before concluding the constraint-based causal discovery part, if we have with FCI an algorithm where we're dropping an assumption, isn't that just like straight up better than PC? And basically, well, maybe in theory, maybe not even in theory. In truth, I mean, if we know that sufficiency is true, there's no advantage on running FCI, because then PC is more efficient and we have a more informative result, right? We don't need to consider all of these possible, maybe unconfounded variables, and we can do rule direction much more efficiency. And basically, since causal discovery algorithms can fail for other reasons as well, independency tests, whatever, you always want to go with a scenario where you can provide the most information, be it by assumptions or anything else, so that you can solve the simplest problem possible. And maybe like one machine learning analogy would be, if you want to approximate a function, but you know for sure this function is linear, why would you train a neural network instead of just mapping a linear function? Same thing here. If we know sufficiency is met, go with the simpler approach. This will be more reliable. This will be better. However, if we don't know it's true, obviously then PC might just be false. So then we use FCI, then we use the more complex model. But that's why both have a right to exist. And yeah, again, generally pick what is the best fit for your problem. There are so many causal discovery methods, many more than I will talk about today. So if you actually want to apply something, doing some literature research is definitely worth it. Okay, this is hopefully understood by now, but just to summarize the general category again, constraint-based causal discovery algorithms infer the Markov equivalence class of a causal graph by systematically using statistical conditional independence tests to prune impossible edges and orient remaining ones based on the resulting constraints. But now maybe like one concise statement on the class of causal discovery methods, because we're now jumping to a different class that is called score-based causal discovery. And here I'll immediately start by the general definition, or like what's it described by. So here the idea is that we try to identify the graph that maximizes a particular score. So we have a scoring criterion, we apply this on a graph and the data set, and then find the best graph according to that score. One way to do that in theory is to iterate through all graphs, because then we can track the score for each graph, and then the graph with the lowest score, or multiple graphs, are the ones that must be true. Perfect. I mean, that works, but as you know from the first lecture, completely infeasible if we scale to multiple variables. So instead, these algorithms are a bit smarter and quite often follow some kind of greedy procedure, but that makes it possible to then actually do it and actually get results even for slightly larger problems. Still, generally, such greedy procedures might risk getting stuck in local optima, although, I mean, the like state-of-the-art methods try to take care of that and should, in theory, avoid that. Still keep in mind that any greedy approach might still risk that anyhow. So I talked about the scoring criterion. Let's take a look at like one very famous one called the Bayesian information criterion. You see the formula on the top. So basically we have k, that's the number of parameters. Here we want that to be low. This basically means that whenever we can remove an edge, we should. And the motivation for that is basically, if we have even the simple example, A and B, both are independent, we can draw an edge between those and still represent the distribution perfectly, right? Like if we only care about the distribution, we can always add more edges. But then there's not really the true graph, especially if we care about causality and interventions. So that's why we would like to have the number of edges to be as small as possible while still representing the probability distribution well. So that's why we want k to be small. Then n, the sample size, number of data points, that's just a given. And then obviously the other thing we mainly care about is the likelihood. So the probability of observing the data given the graph we're currently looking at. If we combine this with minimizing the edges, then the graph that is the best should have the best score as well. For GS, an important property for efficiency is decomposability, meaning that we can compute the score for each node. So for like each function in the SEM, if you want, independently. So you can do like 2 small mathematical steps, and then you can see, okay, we can basically do this node-wise independently. All right. So the algorithm I'm going to be talking about for the score-based category is called greedy equivalence search. And for this, you need some fundamentals, starting with the covered edge, and that should be a 5 on the citation thingy. And an edge is covered if and only if the parent of the like effect variable has the same set of parents as the parent variable, plus I mean that parent variable itself. So in that case here, for the left graph, the edge AB and the edge AC would be covered, and the edge AB and the edge BC would be covered on the right graph. There's a very important intuition between this like definition of uncovered edge. That is that these edges are the ones that in the true MEC, like Markov equivalence class, they basically wouldn't be identified, or we could change them and invert these edges while still staying within the same Markov equivalence class. So if we revert an edge that is covered, then the dependencies and independencies of the graph don't change. And this is a very important step in intuition for the idea of the algorithm, and this is associated with the so-called Chickering sequence, named after the author. Maybe I just quickly read it. So if we have like 2 DAGs such that independencies of one is the subset of the independencies of the second one, then the Chickering sequence is a sequence of DAGs, like step by step, such that we start with one, we end with the other, and each one is obtained from the previous one either by an edge addition or covered edge reversal. So basically, if we add an edge, we can only remove an independence by doing so. But if we redirect the covered edge, we know that we don't change the independencies. So we know that the independencies always only decrease by going through this Chickering sequence. So we can never have like first a larger amount of independencies and then a smaller amount, or something like that. You know, we can only remove or keep the independencies unchanged, but we can never add one. And this paper and the associated research actually proves that there always exists such a sequence if this like initial condition is met. Feel free to take a look at the proof if you want to. I'm not presenting that in the lecture. But with that underlying motivation, we know that there is an algorithm that we can utilize that motivation to then discover the DP-DAG as well, right? Because again, we're looking at the data, we can still not distinguish directed edges purely based on these assumptions. So we again only get a Markov equivalence class and not necessarily all directed edges. Other than that, same assumptions as for PC as well. And there we have a 2-phase procedure. Forward phase, we start by an empty graph in this case. So we don't start with a fully connected one as for PC, but we start with an empty one, full independencies, but then grow the graph by adding edges more and more, such that the data better matches the graph. So this then goes back to the Bayesian information criterion, where we get a better approximation of the likelihood if we have correct edges. And this follows then a triggering sequence. And in a backward phase, we can remove covered edges if that improves the score. So basically, it might be that in the forward phase, we add an edge that increases the score at that particular step, but that later on turns out to actually not be necessary. Then we can remove that in the backward phase, and this provably then results in the correct Markov equivalence class. So example here, start with a graph without any edges, full dependencies, forward phase. It's a greedy approach, right? So we iterate over all possible edge additions, compute the score for them, select the edge that has the best score. And if that score improves the score of the current graph, then we add the edge. If the best score that on this next step does not turn out to improve the graph, well, I mean, then nothing improves the graph. So then we stop. And then backward phase iterates over these steps. Again, we just consider all edge deletions, see, okay, can we delete them if they're like covered, and then select the edge with the best score, but only really delete it if that actually turns out to improve the score. I think in practice, quite often the backward phase is very small, short, or maybe even doesn't delete any edges. But in theory, this is necessary to like get the perfect, provably perfect result. So I mean, definitely do that. We might delete an edge or two, but then once deleting would only decrease the score, we stop here and then we're done. Again, food for thought if you want to think more about it. With this approach, where we're not like explicitly checking for V structures in the same sense, why are they still discovered correctly? All right, let's go an example, same as before. So we add the edge with the highest score if the edge is not covered and undirected. And if the graph has not changed since last iteration, exit the loop. So in this case, for example, first it might be that the edge that maximizes the likelihood the most is that one. Then we get this. The GS algorithm here can just basically direct edges that might not turn out to be directed in the very end. But for calculating the Bayesian information criterion, it needs like some direction. So it can choose one of the Markov equivalence class and then just compute the score for that. Because, for example, we know that having sleep quality to coffee, that edge would be in the same Markov equivalence class, but it would also have the same score as this. So the algorithm can basically be free in choosing that direction, still getting the same score, and then continuing with the algorithm. Now in this backward phase, actually, it turns out, well, no removal would improve the score. So in that case, we don't remove anything. However, we know that like two of these edges are actually like not necessarily true to be directed. So in that case, then we undirect them again because we know that the others would be equivalent. Then we get the Markov equivalence class, which is then the same result as for PC. Yeah, I mean, this is much more difficult to simulate on paper as an exercise, because then you would actually have to like compute different scores. I mean, maybe if there was an exercise, we could provide some scores or something. But yeah, so just believe me on these steps. Questions on the GS procedure? Yeah.
Could you repeat the definition of it?
Sure. Yeah, covered edge. So yeah, I mean, if you just want to brute force it, the definition is pretty simple. It means that both parents, sets of parents connected to the edge, share the same variables, plus obviously like parent of the edge itself. But then semantically, intuitively, this means that if we would reverse such a covered edge in a specific graph, we would have the same independency, same Markov equivalence class. All right. So yeah, score-based methods optimize the score. Independencies are considered implicitly. GS is pretty famous for that. If all assumptions are satisfied, also discovers the true MEC, same as PC. Generally, local optima might be a problem. For example, if you just trivially do hill climb search, that might definitely happen. But like state-of-the-art methods usually definitely take care of that. Because I mean, there's good enough stuff out there. There's a ton of different GES variations that like follow the same idea but make different optimizations or change some assumptions, improve speed, remove the sufficiency assumption. Feel free to take a look at these things, but the lecture is too short to cover all of them, so just know that there are more. Okay, any questions on constraint-based methods generally? Okay, so I think that was pretty fast. So let's maybe take like a 5 minutes break, and then we can continue with the next category of methods. All right, so next section, additive noise models. You'll understand in a bit what that means. So to motivate this category, in these two previous approaches, we've seen like two like quite different categories of methods, but they like in more or less do the same thing just by different means. So we still learn the MEC. In practice, they very often don't give the exact same results, but in theory, given satisfied assumptions, they should return the same thing. And we know that like in full generality, I mean, this is the best we can do. For example, right, let's say this output graph, A is a cause of B, always adds 5. This has the exact same data as A is an effect of B, where 5 is subtracted. Or even like probabilistically speaking, same thing if this is our joint probability distribution. The left graph and the right graph both like perfectly illustrate this joint probability. Both are equally possible without like any additional information. There's just nothing else we can do. So that shouldn't be new to you. However, I mean, what if we have some additional information? What if we can give something else? And for example, let's take this very trivial example. Do you have any idea of like knowledge and assumption on the function space we could place to make this actually fully identifiable? Well, both would be linear, right? You can be very lazy about the response here. It's more of like a motivating example. So let's be really stupid. Let's just say all functions must add a positive number. Ta-da, the right one can't be true anymore. Well, I mean, that works, right? In this example, that's perfect. Obviously, as you probably thought, right? I mean, this is a very like specific restrictive assumption. Just saying, hey, let's make a causal discovery algorithm where every number must be positive. Yeah, I mean, we're not doing that, right? This is very specific. However, I mean, small disclaimer, obviously, if you actually know this to be true, then this is specific, but also true, then do it, right? If you know this to be true, do it, works perfectly, great. But then again, such a specific assumption, probably very unreasonable, very niche scenarios where something like that would actually work. But still, this general idea of restricting the function space somehow that tells us something about the causal direction, even for like Markov equivalent graphs, dependency test based, is the idea of functional models, and then also of the one we're looking a bit more at here. Namely, there is something that is much more subtle and much less restrictive that is used a lot to do just that, and something that we actually have on almost all real-world data sets, at least if we have continual variables, namely noise. Sorry about that. So if we specifically assume that we have an additive noise model, meaning that noise is purely added on top of the actual function, then we can do a lot of stuff with that. And this family of models are called additive noise models. So an additive noise model is a particular type of SEM where the structural assignments all have that form. So we have a function, takes as inputs the parents, as usual for a causal graph, returns some value, whatever. But then this function is deterministic, and then the randomness comes from an additive noise term that we put on top of that. And again, this is a restriction, right? The noise term might not be additive like in reality. In that case, we don't have an additive noise model. In this case, this doesn't work. In full generality, again, we have to stick to the MEC Markov equivalence class. But this definitely, in my opinion, and in many other opinions, seems like a much less restrictive assumption where we can do a lot more. And yeah, so additive noise models that form. All right, so let's see how we can utilize that. Let's say we have our data, x and y, and then we have two possible regressions, right? Let's assume linearity of the true function. Then either y is a function of x, so y equals bx plus noise, or on the right, x is a function of y, x equals by plus some noise. Now in this Gaussian case, the blue part of the graph shows how the distribution looks like, mapping y dependent on x, and then we can observe the noise on the right. Do you have any idea on how that would vaguely look like if we do the other way around? If we switch x and y on the same data? Well, trick question, I suppose. Basically the same. Obviously, if the linear function is different, then the one might go up, the other might go down. But especially in the noise, not a lot will change here. And that's because if we have Gaussian noise, this is more or less symmetry equivalent, at least for linear functions. But then, I mean, this example is not very useful by itself, but obviously I have a reason to talk about that. So if we now consider a different type of noise, namely uniform noise, right? So in that case, the noise is not more frequent, very close to the actual function, but it's distributed uniformly in some interval. Then if we map y on x, then we can observe that. And then the noise distribution here basically forms a square, right? Like for every point, it could lie somewhere within a specific interval on top or on the positive or on the negative side. Now, having seen the Gaussian example and now the first uniform part, do you have any vague intuition, idea, or just guess what might be different if we now regress y on x on y, so the other way around? All right, let me show you. So in that case, I mean, we can just simply do it and we get this result. Why do we get that? So for one, basically, I mean, we're just rotating the axis visually, right? But now this means that the linear approximation here doesn't cut through the middle of this noise area, right? Like on the left part, it's always in the middle of the noise block. But on the right part, we see that for negative numbers, there's more noise below of it, more on the negative, and on the positive, there's more noise on top of it. So then this actually changes this noise distribution if we map it there. And crucially, the noise is no longer independent of y, as it was on the left side, right? On the left, it was independent of x, but if you regress like that, it's not independent of y. Yeah?
Why does it not cut through the noise section equally?
Because if you apply regression on that, that's the function outcome. So
but if the noise initially is perfectly uniform, then
yeah, but it's only uniform in one direction. How to explain that?
what's the reason for it not being uniform anymore after reversing it?
So what the regression does, right, is for every vertical slice, if you will, takes a look at the error that a function would have, and then tries to find the optimal function. Now, if you would instead have this function that slices through it here, it would actually turn out that now if we take a look at the errors here, we would have much higher errors here, and overall, this would be a worse approximation. I'm not sure if you have a better intuition to explain that.
So I mean, you for example, assume that the left side is the true generating process. And now if you take the above equation, right, where y is given bx plus some epsilon, and then you transform it, rearrange it to solve for x, like it is done on the other side, then you basically will see that you get this other form where this epsilon has this factor of y attached. So just from rearranging the formula, like solving for x, you will just find that the noise is no longer independent, and basically this explains this behavior.
So in both cases, the red line is the optimal regression result. It takes a while to get your mind wrapped around that, at least it did for me. Obviously, it's worth it if you manage to. So feel free to think about that more after the lecture as well. Well, we'll actually have an exercise on that, even better. So if you understood intuitively, well, perfect. Otherwise, for this lecture, also like kind of fine to just accept that to be true. Obviously, again, think about it. Helps to really intuitively understand it. But for this lecture, if you just believe it to be true, and then you can still understand how the other methods that I'm going to introduce in a bit will work. So yeah, starting with like a basic idea on how we can now leverage this phenomenon. So we have an edge. This could be either xy causing xj or the other way around. So we're fitting functions for both directions. We save the residuals, so like the like noise offset, and then testing between dependence between that and the covariate. So what we just did before, right? Where I said the noise is no longer independent of the variable, and then choose the direction where the independency holds. In this example, noise must not be Gaussian. In full generality, it could be Gaussian on exactly one, but not more than that node, but there's like more of a technical detail. So yeah, with that, let's take a look at like really the specific causal discovery method that does that, called linear non-Gaussian acyclic models, short LINGA. So the assumptions are completely in the name. Input dataset as usual, but now importantly, compared to the methods we looked at previously, our output is not a ZPDAC, not a SAP, not a PEG, but actually a full directed acyclic graph. So to take a look at the assumptions like in full specifically here, each variable must be determined as follows by the parents. This is an additive noise model, but that's a more specific additive noise model, because here the functions are linear, right? We have like that each parent has like this covariate bij, so a linear influence on the variable. And then we have a constant offset as well as noise. And the noise here must be non-Gaussian distributed with non-zero variance, because if we don't have any variance, we can do the trick. And independent of each other, this noise being independent of each other basically mostly resembles the causal sufficiency assumption. Because if that would be dependent from each other, we might again have like unobserved confounding. But yeah, this can basically all be described by this single equation. And then the idea behind LINGA is to disentangle noise using independent component analysis, and then leveraging this fact about this like Gaussianity of the noise, and then the central limit theorem in particular that says that if we have different distributions that might not be Gaussian, that are not Gaussian, but we like add those up and up on top of each other, then they will turn out the like sum of this distribution will turn out to look more and more Gaussian. And then following this idea, the further down, like in a graph we are, the more noise distributions we stack on top of each other, the more Gaussian the distribution will look like. So if we like can sort by Gaussianity, we can identify that. If you have questions, give me like one more slide. Or like 2 or 3 more slides. Let me finish LINGA. So let's go over the mathematical details here. So our setting could be put in matrix form, x equals bx plus e, where b basically then represents like the adjacency matrix of a graph. And then we can write this as x equals ae. So basically then, so our equations are like x has some noise, x2 depends on x1, has some noise, x3 depends on the previous ones, has some noise. This can be written in matrix form, where we have the coefficients in the matrix. And then by substituting the variables on their parents, on their ancestors in general, we can substitute x1 into x2, right? And then x2 is a n1 plus n2. Do the same for x3 or any other variables for that matter. And by that, transform this into a matrix multiplication where we have only one matrix that needs to be multiplied with the noise. So then we have the AN representation where x basically is only written with respect to the noise. And now this is exactly the input we can use for ICA, for independent component analysis. And just to get the idea here across, so let's say the first box on the left is our original distribution, S1, S2. These are somehow mixed by A, by like some matrix, but then ICA disentangles them again. And this happens, as I hinted at previously, using like the central limit theorem idea, that the further, like the longer our chain is, the more Gaussian the components become. So if we search for like the most and least Gaussian distributions, we can then in theory use that to figure out like how far down the nodes are in like the causal hierarchy. And then again, going back to the Gaussianity example, if you take a look at ICA for the Gaussian distribution case, I mean, even if that's rotated, if we wouldn't have the colors, right? The colors here are the ground truth unknown to us, more or less. If we wouldn't have the colors, these look the same. Like we can't do that. The non-Gaussianity assumption here is quite important. Yeah, like 2 more technical steps. So this gives us now these like disentangled representation, but then because ICA basically has like some kind of permutation ambiguity, this means the rows might not be in the correct order. Not being in the correct order in this case means that they might not align to like the correct noise variable. So you need to take care of that. How can you do that? Find a row-wise permutation such that no zeros lie on the diagonal. Why is that the idea? Okay, right. For A, we know the diagonal should be like some multiplicative factor. We know zeros should be somewhere where no edges are. So if we have a like permutation, like a permuted row order, it might be that we get the first row instead of on the third one, then there would be a 0 on the diagonal, but we know this can't be the right order. So that's why we want to like not have any zeros on the diagonal. Yeah. And then we still have to like scale it because ICA is often a scale invariant, normalize the diagonal to 1. And then from that, we can subtract the, subtract the matrix from the identity matrix and get our desired B. Another problem that we have to deal with here, this resulting graph might not just simply be a DAG. It could be if everything went completely perfectly. But you probably have to do another operation to like find a permutation that is strictly lower triangular. So acyclic so represents a DAG. Why do you have to do this? That is because both steps are probably on real world data not completely exact. You probably have at some places where the number should be 0, some like epsilon of 0.0005 or whatever. So what is actually done in both of these steps is instead of solving this simply algorithmically, you have an optimization problem to solve where you say, okay, like these numbers that we want to be 0, they should be like as small as possible. Same for the strictly lower triangular matrix. You probably don't have enough zeros, but then you want to optimize such that the like upper triangular matrix is as small as possible. And then basically you assume that these small values were just due to noise, should be zeros, remove them and use the rest as your DAG.
Questions. First of all, maybe this is trivial, but how do you measure Gaussianity?
Tests? I'm not sure.
That's how you assign the score, right?
Yeah. I mean, yeah.
Is it like you measure how well it fits a certain Gaussian distribution, but then the question is,
yeah, how well you can map a Gaussian distribution on that given like data, right? How likely it is that this data is like sampled from a Gaussian distribution.
how well can you fit it with a given?
Yeah. And yeah, I mean, obviously, right, if you do that, you don't just get yes, no, but you get some score, some confidence. So that's why the like noisy results might be there.
You have to set some sort of threshold.
I mean, you actually don't really set a threshold per se, but then you optimize the like, try to optimize the noise away in the last step.
Question in here exactly at the very end, we have the 2 post-processing things that we have to do. First, normalize diagonal to 1.
It's just ICA consequences, basically, yeah.
Or the permutations, both of the permutations. Are there efficient algorithms for these, or?
Yep.
Oh.
I mean, I'd need to look at what exactly is done instead of the art stuff, but yes, exactly. Right. 50 more minutes, right? Okay. So another additive noise model algorithm is RESIT, regression with subsequent independence tests. Here the set of assumptions is a bit different. We have acyclicity. Here we have nonlinear functions, additive and independence noise, and like sufficiency. Our output is still a DAG. Noise now can be Gaussian, but functions must not be linear. So that's a like trade-off we have here. General idea here, we first identify the full causal order topologically. So every node is a cause of every successor. And then remove unnecessary edges. So like very small example, phase 1 would get some fully connected graph, but some directed fully connected graph. So here we would have the order A, then B, then C, then D. But I mean, the true graph might have fewer edges. So in the second phase, some edges are removed. Ta-da. And I mean, this might be the true graph. In a bit more detail, what is done is for determining the topological order, we regress each variable on all other variables. And then having done this for everything, we choose the variable with the minimal dependence between residuals, so the like noise, and the predictors as the last variable in the causal order. So like it's called sync node in the paper if you want to look at that. Yeah, and then like iterate over that until you have the causal order. So yeah. Basically, again, the idea is we have a dependency to the previous variables if they were responsible for causing that variable, right? So if we have a full independency to all others, that must be like the root cause. So this way we can get this like causal hierarchy by taking a look how dependent or independent even these noise terms are from their predecessors or like descendants. And then for removing, we have the full topological order, iterate again, iterate over basically each edge, so over all like parents. So we take a look at one node, take a look at all their parent nodes, and then ignore one of these parents, just like trying it out, and regressing on all but that parent. And then if it turns out that the residuals are independent from that parent, we know that there actually shouldn't be an edge there because there's an independence, it doesn't change anything. We can remove that edge and we're good. Questions? I know this is a bit much. Hopefully it's like
write everything down.
well, I mean the slides will be online. I have a bit more time if you have like a specific question, maybe.
Is that relevant for the exam?
Shut up. Yeah, I guess I shouldn't answer exam questions. So like exam relevancy questions.
Yeah, so I mean, the idea is to give a high level overview of these methods. So we might ask on like specific steps and so on, but we like won't ask you to like perform these algorithms.
I mean, not RESIT or not Linga.
Yeah, like at least not the later ones. For PC and GS, we will provide some examples of some exercises. But for these later ones, it's enough if you like roughly got the bigger idea.
So basically, I'm not saying this will definitely be enough for the exam. It might not be. But if you can, for each algorithm here, summarize it in one sentence in such a way that no two summaries are the same, that's a pretty good start. You know, that means you'll have like some basic idea of how these algorithms differ. Doesn't mean you'll get like the perfect grade in the exam with that, but that's definitely like a good start. And if you can't do that, maybe take a look again or like ask questions on the lore in another lecture. Okay, but I can calm your nerves a little bit. Now the last part of this lecture will be even more high level. I want to give you an overview of like what's out there. Still not exhaustive, there's too much, but just like the general categories of causal discovery methods. So that's why I'll go over like other genres, if you will. But here I really give like a one-sentence summary on each. And then if you're like curious or interested, feel free to read up on it. But otherwise, I'll not go into any detail here. Okay, last bad joke of the day. So actually, there's another very math-heavy approach. Can you handle that? And then I have to specifically ask you for no overreactions or emotional outcries. If you manage to promise to won't cry, that's perfect because the method is called no tears. Yes. Basic idea, we're solving a combinatorial optimization problem, but transforming that into a continuous program. So we have like minimize some score such that the resulting graph is a DAG, but this is transformed into an optimization problem where this like such that this is a graph can be calculated like mathematically efficiently and most importantly then allowing for gradient descent. Now gradient descent right from deep learning, neural networks, and if we can transform our causal discovery problem as a gradient descent problem, that's obviously quite good for efficiency. So that's the basic idea here. And just so you've heard of that, Dagmar is now a like newer version of that. So Nautilus from 2018, Dagmar from 2022. It does some things differently, like with the mathematical details on how this is achieved, but the idea is exactly the same. I mean, like not exactly, obviously, but the underlying idea is the same. Yes.
Just one note. So they all the methods before, they are specifically causal discovery methods. In note here, they are very careful to call it a DAG discovery method, because before we were leveraging properties of the noise and independencies, and here it's really like fitting the data according to a score, and it gives you a fully directed graph. So and we know by these theoretical results we have seen before that in some cases that can't be, like there are unidentifiability results for additive noise models with linear equations and Gaussian noise. And this method would still give you some graph, but be aware that this might not be the true graph, but just the one that fits the data best.
And I believe you're gonna talk more about like related topics next week in the lecture anyhow.
Yeah.
Right, so we can have different sources of knowledge that we haven't really discussed yet in the previous methods. For example, expert knowledge, right? You could have specifically know some edges but not others, maybe know that some edges couldn't be true, have some information about the causal order, and like different algorithms can like implement these, maybe provide less background knowledge or use it elsewhere. Very big recently is the LLM topic, because there we can query LLMs, can be very like efficient and automate this. The potential of these methods is obviously quite high. It's a like different source of knowledge, but they not exclusively, but mostly don't take the like numbers in the data set, but mostly the semantic information about the variables, something that's not leveraged by the methods I've explained before. But again, it's like difficult to really put this in one single bin because there's like very many different approaches on how LLMs could be leveraged or like included. For just to list some examples, if you take a look at like purely based stuff, you could like just vary each pair of variables. Does that cost that? You can, I mean, the naive approach is basically just prompt the LLM with the full problem and be like, give me the graph. Depending on the problem, that might work. Or there can be more sophisticated strategies where you iterate like the variables in like some specific order, prompt in a specific order with a specific strategy to be like maybe less biased, hopefully more efficient, and yeah, a bunch of stuff out there. Also hybrid approaches, for example, right, you could like just do both causal discovery and then LLM predictions independently, but then like train a separate predictor on top of that tries to like take the best out of both worlds. Maybe that works. You could actually run the PC algorithm, but don't use independency tests from data, but on LLM outputs, ask the LLM, should these two variables be independent when conditioned on another one? That's something that's been done before. Or you could like use some other meta information, query for different types or tags, you know, like what the variables have in common, and then try to make use of this common information to direct more undirected edges. That's only like some examples. Maybe one a bit more meta is the Causal Copilot. That's again on the more meta level. So here they're basically using an LLM to guide the entire causal discovery process, trying to select the right approaches and like parameters and all of that. Especially if you actually want to do something, I guess it's not a bad idea to just play around with that a little bit. But yeah. Then you've heard about time series in lecture 3. We haven't talked about that here so far, but there are also like a bunch of different approaches where you can apply causal discovery on time series. Quite often, these are inspired by like non-time series versions of causal discovery methods. For example, PCMCI is pretty like famous. algorithm that like then has obviously different assumptions, but can then predict graphs for time series. Another one for lingam is called var-lingam. For node tiers, dino tiers, just know they exist, and obviously that they have to like take different assumption scenarios into account. But it's being done and it's quite relevant, especially if you look at like some real world stuff as climate problems or data. Because in the previous non-time series settings, we basically have an IID assumption. But then again, if we have like time series data, we could still apply this IID assumption, but I mean, this can't be correct, right? So if we actually have approaches that are tailored for the time series setting, making use of that information, that should be better in these scenarios. Now on the acyclicity assumption, there are basically two general strategies on how we can still do causal discovery if we have cycles in the graph. One is exactly that time series setting. If we have time, then this kind of can resolve cycles in a way, right? We can like say, okay, A causes B and B causes A, but there's always like a lag. Then we can still observe them. There are multiple different ways, but just know that obviously time series is like, in time series, acyclicity and cyclic relations are a big topic. There's another direction that doesn't consider time series, but has to make another assumption. That is that we're basically assuming that the data we're observing has converged to some equilibrium. So if we have like a variable that causes itself only, then we would assume that like this happens, I don't know how many times, but then reaches some equilibrium. This is the state that we're measuring. This is the data that we're measuring. And then we can also do like some specific, not deseparation, but related approaches and procedures to try to deal with cycles. But obviously this is more difficult. If you have the acyclicity assumption that it's true, don't worry about any of that. And yes, lastly, I really just want to say, if you've played a bit around with causal discovery, you would know that the algorithms can only give you results that are as good as the data they represent. I mean, if you have 5 data points, your dependency tests won't be reliable. I mean, you just get random results probably, or definitely very unspecific, unreliable ones. These algorithms, most of them are guaranteed to give you the correct results if the assumptions are satisfied, but given finite and noisy data, that might not always be as good. Obviously, these algorithms are still very, very useful, used a lot, but I mean, just because you get the wrong result doesn't mean the algorithm did a bad job, just means the data might not have been good enough. And there are, yeah, for example, dependency tests. And on the other hand, it might even be that they make the correct prediction, but for the wrong reason, which might then fail in other scenarios. So that they're like following a logic that works in some scenarios, but not in others. That's a topic that's going to be covered more next lecture. So if you have questions, please wait until next week there. I just want to mention that here is such that like everything causal discovery is like mentioned once in a lecture. But if you have more questions there, yeah, Moritz will let you know something next week. Right. So we had the Mensa graph exercise earlier, and now I'll finish with another exercise for you to think about until next week. Imagine you're in a real-world setting, you have your data set, you want to apply causal discovery. Now in this example, in this exercise, you know how the variables have been measured. You know that they have all been measured like at a specific point in time. So there is a clear temporal order, and you basically for each variable know that one variable came before the other or was measured before the other. Now then, in this case, also assume that causal sufficiency is given, is true. Now argue why or why not independently based causal discovery methods can actually or should actually be able to return a full specific DAG and not only Markov equivalence class here. Yeah, if you understood that, then well done. And we'll talk about that, or Moritz will talk about that next week at the start of the lecture. Hey, I made it in time. Any more questions? Well then, I mean, briefly, so summary, you don't need to read it out loud. Nothing new here, but some summary on one slide. Yeah, anything you had in mind to ask, clarify, comments we should maybe repeat next week? Well, then, thanks for your attention and see you next week.